Okay, any combination we can take here, and with this single qubit, we can generate n number of states out of in here. So basically, this is the state vector we always take, alpha 0 plus beta 1. In X gate, what it does, it converts this 0 into 1 and 1 into 0. Whatever state it will get, it will just flip it out. So at the end, we get alpha 1 plus beta 0. Okay. So this, but the amplitude, you keep in mind that amplitude stays intact. Okay. So it just changes this particular state. This particular qubit, we can say that this is flipped from 0 to 1 and 1 to 0. X gate is simple. Z gate, what it does, it is a phase flip gate. X gate is a bit flip gate because it converts 0 to 1 and 1 to 0, bit flip. And phase flip means it changes the sign. So it starts with alpha 0 plus of beta 1. It just changes alpha 0. It keeps alpha 0 as it is and changes the sign over here from plus to minus and beta 1. Okay, this stays same. So in the matrix representation, you can see over there, in the Pauli X gate, the first vector 0, 1 is 0, 1. Okay, so that represent, so what we can say, 0 is written as 1, 0. Okay, that we know from our previous session, and 1 is represented as 0, 1. Okay, so instead of that, in Pauli X gate, if you see in the matrix form, instead of 1, 0, it is written as 0, 1, and 1 is written as 1, 0. Okay, so that means it converts the 0 to 1 and 1 to 0. And in Z gate, if you see 1, 0, the first 0 qubit is 1, 0, the vector for 0 is 1, 0, and for vector for 1, now it is converted into 0 minus 1. So that means there is a phase flip. So this is also known as phase flip gate. Now, the Y gate, it is a little complicated. It's just a combination of X and Z gate. It is a bit and phase flip gate. Okay?
Yes, you can use this.
Okay. Okay. So what it does, as you can see very clearly, alpha 0 is converted into iota of alpha 1, and beta 1 is converted into minus of iota beta 0. Okay, so just a phase also is getting changed, and iota is coming into the picture over here. Okay, and the next one is Hadamard gate, which is a superposition gate, converts any particular state into a superposition state. So 0 is converted into 0 plus 1 by root 2, which is also known as plus state. Okay, and 1 is converted into 0 minus 1 by root 2. Okay, and earlier also in the previous session we have seen that 0 and 1, we mostly use these basis states. Okay, and we also in addition to these basis state, we also use plus and minus. These are the diagonal basis states. Okay, and but just that we have to check that whatever basis states that we use, that needs to cover the entire vector space. Okay, and it can generate each and every state with the combination of these basis states. We can generate any other state. Okay, so that's why we use these mostly. And the next one is, these are the very basic gates that we have. What is not changed? Okay. So these are the very basic gate that we have. And the next one is the multi-qubit gate. Okay. So so let's go on to the multi-qubit gate. Multi-qubit gates, there are two main important multi-qubit gates. C-node gate, control node gate, and the swap gate. Okay. So C-node gate is a control node. Whenever the control qubit is in state 1, the target qubit gets flipped. Okay, so that is our control node gate. And the swap gate is, as the name suggests, it changes the qubits. Okay, it started with x, y. X is on first and y is on second wire. At the end, after the swap gate, it gets flipped. Okay, y goes to the first qubit, first wire, and x goes to the second wire. Okay, and those are the matrix representation related to those. So as you can see over here, in between states are getting converted. Those are the, if we convert into basis states, we can clearly see that, okay, those are getting swapped. Okay, but what is happening? Okay. क्या हो रहा है? Here I'm seeing rotation gates, and there I'm seeing, okay, now it is okay. Okay, so next,
I think it is, as it is from Google Meet, ma'am, it has a delay of 2
Okay.
seconds.
Okay, sorry. Okay, so other than those Harama single qubit and multi-qubit gates, we have rotation gates as well. Actually, I'm showing you these gates. Later on, we will see on Composer how we, using these gates, how do we create a state, any state vector we can create. Or later on, when we go to the algorithmic part, there we will use these gates. Okay, so that's why just as of now, I'm just showing you these are the important gates that we need later on. So these are the rotation gates. So so as we have seen already, Pauli X, Y, and Pauli Z gate. So corresponding to those gates, we have these rotation gates. So rotation along the x-axis, rotation along the y-axis, and rotation along the z-axis. But in mathematically, how do we write it? Exponential of minus of iota theta by 2x. Okay, and the theta by 2 is the angle that we consider over here, because I think Aniket must have told you about it, because on the block sphere, here is the 0 and here is the 1. Okay. So this is the case. Okay, but here there is a difference from 0 to 1. There is a difference of 180 degree, but we consider it as a theta by 2 because those are orthogonal to each other. Okay, 0 and 1. If we do a inner product in between 0 and 1, then we will get 0. So these are orthogonal states. So that's why we just keep this angle as theta by 2. Okay, although there is an angle of theta, but we just keep it theta by 2. Okay, so that's why it is exponential of minus of iota theta by 2x. Now, this once we solve this exponential, and this is using Euler's theorem, we can solve it. Cos theta identity minus of iota sine theta x. Okay, so we put x over there, and then what we can do, suppose okay, this is exponential of minus of iota theta by 2 x. So cos theta identity minus of iota sine theta x. So here we put x over here, x matrix over here, identity matrix over here, and just solve this equation, and we will get that particular matrix out of it. Okay, now this theta, we put this theta value over here. Okay, any theta value on which angle we want to rotate our qubit. So, okay, so if we want to rotate our qubit along the x-axis, then we put our theta, whatever angle that we want to rotate, so that we put over there. So these are the, actually also known as, this theta parameter is also known as parameterized gates, and which are very useful in quantum machine learning. Okay, so these are the basic. Okay, and the next one is the very basic phase gate, because in the earlier, in the rotation gates, the theta parameter is not fixed. Okay, other than that, if we fix the gates, those gates are also known as, there is a specific term for all those gates. Like we have T gate if our theta parameter is pi by 4. We have S gate if we have theta parameter pi by 2. We have Z gate. If the theta parameter is pi, then that state is that just gates is known as Z gate. Okay. So I just okay. I'll just show you how these gates on the block sphere, how these gates will look like. Just note down the names. You will find everything on internet. Okay. So I'll just show you. First of all, I'll go to composers. So just to show you how this composer, IBM composer looks like. So on, if you no, the Z gate is same. Just you put, you just normalize it. Huh. But we declared Z gate as 1 by root 2. 1 minus 1. Yeah. Just later on, if we normalize it, then it will just equal to that Z gate only. Okay. So for the composer thing, if you just go on Google and search for it, IBM Quantum Composer. Sure. IBM Quantum Composer, you will find that link, Composer IBM Quantum Platform. Okay, just you have to log in on that. Any email ID can work for that. Your institute ID, anything. You can log in, register with that email ID. It will not ask you anything. Okay. This IBM Quantum platform, this composer thing. Okay. Okay. If it is slow, no worry. I'll just show you how this composer will look like. Okay. Huh? Okay, yeah, you have got that. But once you run your circuit, okay, that time you wouldn't be requiring your email IDs. It will ask for the registration if you have not done it. Okay, so let's see how this composer thing looks like. Okay, so this is the playground that we have. Here we will just see what we can create. Okay, by default, these are the 4 qubits it is starting with. And this C4, it is written over here. This is a classical bit. Okay. Once we do the measurement, the quantum bits, whatever quantum state that we have, that will deprecate and will convert it into a classical. It will give a classical bit us. So that classical bit will be stored in that classical register. So for the time being, not for the time being, in programming as well, we will call those Q0, Q1, Q2, Q3 quantum registers, and this classical bit, we will call it as classical register. Yes, that is very simple. And the first one important thing that we have to always keep in mind, this circuit will always start with the state 0. Okay, it will always start with the state 0. If we want to convert this into another state, we have to apply some gates over there. Okay, so let's move on. Okay, so you saw your playground. So these are the operation, these are the gates that we have. So these are the very basic gates it will provide us that we can use to generate some of the circuits to do some kind of operations. Okay. There is Hadamard gate, and this is the C0 gate. This is a C0 gate, which is Pauli X gate. Okay. So just this particular gate, we have to keep in mind that Pauli X, instead of Pauli X gate, it is providing us the NOT gate. And this is a C0 gate. Another one is Toffoli gate. I've not shown you what is Toffoli gate. Toffoli gate is CC NOT gate. Control NOT gate. That you must be knowing that if we have a control NOT gate, there is only one control qubit. Another one is target qubit. If we have two control CC NOT, that means we would be having two controls and one target. Whenever those two controls would be in one state, one qubit, and then other target would be converted. Another one is swap gate, identity, and all those gates, phase gate, T gate. Other advanced gates are also there, RXX gate. Okay. So RXX gate is a multi-qubit gate actually. Okay. So not in the sense of actual multi-qubit gate, but for that case, instead of 2 by 2 matrices, we would be requiring 4 by 4 matrices. Okay. Okay. So if we go come down, these are the probabilities we will see here. The probabilities we will see here. Okay. So as we can understand from here, alpha 0 plus beta 1, alpha and beta are the amplitudes. Once we measure it, we will get the probabilities, alpha square, beta square. Okay. So those, what is the probability corresponding to 0 or 1, that we will be able to see over here. Okay. Right now, it is showing that probability is 100% 0, 0 because every state is in 0. Every qubit is in 0 state. So it is showing us the 100% probability. And this one is Q sphere. Okay. So Q sphere is a little different from block sphere that we have. Generally, in theory, we just talk about block sphere. And okay, in block sphere, we only talk about single qubits. Okay, the qubits which is on the sphere are the pure states, and which are in the sphere are the mixed states. Okay. So, but in Q sphere, we can visualize 5 qubits. Till 5 qubits we can visualize how those states are getting rotated, what is the angle behind it. So all those things we will be able to see over here. Okay. So, and this right side, we have this, some programming is written over here. So by default, it is an open QASM. Otherwise, you can change it to Qiskit as well. Okay. So Qiskit would be easier to see over here. So here it is showing us from Qiskit, import quantum register, classical register, and quantum circuit. Okay. So what we are doing over here, we are importing quantum registers. Of course, we require quantum register to use qubits. Classical register because we, of course, after measurement, we're gonna store those states. So, and using those quantum and classical register, we're gonna make a quantum circuit. So we need all those things. And NumPy is just for basic calculations we are doing. And what it is doing over here, in the next line, it is kind of creating a function. Okay, quantum register, and for quantum register, it is providing 4. 4 means 4 qubits, and for classical register, 4 bits for classical register. And using these quantum register and classical register, it is creating a quantum circuit. Okay. Till this, everything is clear. Every basic points we are only talking about. Okay. Let's move on. Let's try putting some gates over here. Let's see how it changes. Okay. So just I'm dragging and dropping Hadamard gate over here. So I would suggest that let's start from a 2 qubit. We'll not go for the multiple qubits. We are just starting with the 2 qubits. Okay. If we are working with 2 qubits, we would be requiring 2 classical registers. So you can see over here in the probability section, 2 qubits means 2 power n number of bits we would be getting. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. Combination of zeros and ones. If we increase the number of qubits, we would be getting those many. If we are giving 3 number of qubits, 8 number of bits we would be getting. So these are the things. Okay. So now let me just keep it 1 qubit. Okay. Any problem? Yes. 2 qubit. Okay.
I have taken Hadama.
Hmm.
So you have said that 2 qubit.
2 qubit. I'm just.
How?
Okay. Either we can add or we can delete. Okay. So, what? Which screen? If I'll.
Ma'am, for exit is giving us.
What you guys are doing? What happened?
They are not visible, ma'am. The font that is.
Actually, okay. Is this okay? If I'll do this, and some of the part will be visible and the entire screen would not be visible. The entire composer.
Ma'am, can you make it only 100% as it is?
Okay.
So that I'll try here. Hit 100%.
Sir, those 2 arrows are there.
Yes.
You can that is for exit. Okay. So, so you are presenting, right? I'm not presenting over here.
Actually, you are presenting.
Uh-huh.
You are telecasting that.
Okay, okay. So that's why.
You are presenting actually.
Uh-huh. Okay, so you.
A code we have to
Mm-hmm.
here.
Okay.
Left.
So that they can see the code.
So, okay. It is not required for the time being. Code is not required. Just this composer part. Okay. So if you can see over here, I only have 1 qubit. Q0 is there. Okay. And this is the probabilities over there. So this is 0. Okay. Now let's apply Hadamard gate on this. See, probabilities are changing. Okay. So that means we have created a superposition state. Understood? Okay. So if you go over here, it will show you that this is 0 is with 50% probability and 1 is with 50% probability. Okay. This we can see without even measurement. Okay. Now let me add another qubit. I'm adding it. Okay. From the plus sign, we can add it. From the delete sign, we can delete. See, the probabilities are shifting from 0. Now, earlier it was only 0, 1. Now it is 0, 0, 0, 1, 1, 0, 1, 1. Although there is nothing in 1, 0, 1, 1. Because the first qubit is empty. We are not doing anything. Now what is happening over here? If you just focus on this is 0, 0, 0, 1, 1, 0, 1, 1. Okay? 1, 0, 1, 1 are empty because we are not doing anything on Q1. We are just applying Hadamard gate on 0th qubit. And now this thing we have to keep in mind that this one is the left hand side. one is the qubit 0 and right hand side one is the qubit 1. That represents corresponding that particular bit correspond to qubit 0, another one is correspond to qubit 1. Thus there is a little this difference in Qiskit. In whatever we are reading, we just go from left hand side to right hand side, right? But in Qiskit we just go just the opposite. Okay, this we have to keep in mind while working with Qiskit. Okay. So let me just apply a C0 gate here. If I'll apply a C0 gate from Q0 to Q1, as Aniket has told you, that it will create a superposition state. Oh, sorry, Bell state. Because we have already created a superposition, it will create a Bell state. Okay? Let's see. The probabilities are changing. Instead of earlier it was 0001, now it is from 0011. Okay? So in this way, we can also create another states, another Bell states as well. Okay, we just have to apply X gate and Z gate, combination of those. That's why Pauli gates are so much important. Okay, so so this is clear. Now let's see if we can go for a run for running this circuit. We have to do a measurement in that case. But we will not run it because for that we have to go to IBM systems and it will take hours to run. Okay, so for the measurement we just take put this gate over here for the measurement, and this is also we are changing. Okay, although the probabilities are still in 50-50% because we have not done a proper measurement of it. Okay, so in the similar way over here, if you see, earlier we have seen till this point only. Okay, in programming. Now what we have done is we have added some of the gates. Now this program has also changed. Okay. So you can see Hadamard gate and CX gate also we have applied. So circuit.Hadamard in small we have to write and circuit.CX gate. These are the notations that we have to remember. Okay. And dot measure for measuring the qubits. Okay. Okay. Now let's go to IBM hardwares. Is everything clear till now? Okay. Now if you click on setup and run, if you click on setup and run, there are some of the parameters that we have to keep in mind. For setup and run, account is needed. Okay, so that's why I asked you to create an account, but of course, you don't have to do it right now. You can create it later on. Any email ID, whatever Gmail ID you have, or your institute ID you have, any email ID can work. Q0 or Q1 are the inputs. C1 is the classical register. Yes. Q0 and Q1 are the quantum register. C0 and C1 are the classical register. It will increase. So that's why.
In which case it is using this circuit.
This is classical register.
Register.
Classical register. It is not quantum. So it will just help us in seeing these all basic states downstairs. That particular. Okay, but it will not help us in anything.
Showing the cross
Probabilities result, probability result. Okay.
probabilities and state vector both are.
State vector.
Means that
Probabilities.
Population before measurement, the probabilities will be
Yeah.
and state vector means after measurement.
Whatever the state vector is, actually, that will be shown to us. Probabilities are the easiest to see, so that's why I've just shown you the probabilities. Yes, and this is correct, but just because this classical register is just increasing these basis states, so if we just keep it equal to the quantum register. Okay. Oh my god. Huh? Uh-huh.
Classical bits how to add.
Okay.
Measurement is not there.
Classical bits. How it has gone? I've never seen this kind of thing.
We are getting so same error.
Okay, so what could have happened that you do not have any account on this, so that might also be a problem that you are not allowed to add.
Yeah, after they have the 20, 30 days trial also.
Huh.
it? Oh, signed it.
You have assigned it.
Oh, yes, yes,
It's already there. Okay, it might be some kind of glitch. There is no internet.
I'll see that. It should
Huh.
be there only. Yeah?
It should be there. Might be some kind of technical glitch. So, due to internet, that problem might be coming. Due to the internet. Okay. So, try to refresh it. If it does not come back, then let me know. Okay. Yes. Get up and help me out.
Yeah, whatever the output you are showing there, we are not.
So this is the okay. I'll tell you. There is one problem everyone is facing. I'll let you know what is happening. So in this case, in the classical register, if you increase this classical register, this is C2. Okay, this is C2 because there are 2 qubits I have. Try to decrease this C2. If it is showing C3, C4, that means you have more classical bits. Okay. So because of that only, you are getting these many probabilities. Okay. If you have C3 over here, that means 2 power 3 number of probability basis states you will get over here. See over here. Not the basis state, the probabilities you will see over here. Okay. Okay, so let's go to setup and run. So in setup and run, so this is the thing. There are 2 QPUs we are able to see over here. Okay. There are 2 QPUs with different number of qubits. Okay, one is with 127 qubits, another one is 133 qubits. Processor type, in today's morning lecture, Kapil sir talked about Eagle and many other processors IBM has actually. So these are the processors, okay? And the status. Status is, okay, so this is, this Brisbane is post, it is for maintenance. Of course, you can, this is the very basic things that you can see. Okay, total pending jobs. This is the important one. Total pending jobs. The Brisbane is saying 2,000 something pending jobs are there. So if you will submit your job right now, so that particular circuit that you have, that is your job. You want to run that job on your quantum system. So there are currently 2,000 something pending jobs over here. So yours would be 2044. Okay. So you have to wait for those many jobs to complete before your job to get in. Okay. So it's better if you go for the less pending job, of course. So that's why I told you that if we run it, we will get hours of. Okay. So another thing is shorts. This one, shorts. You can create it, or you can just look into it. I'm just showing you what is happening because I'm also not gonna run it. It will take a lot of time. Okay, shorts are the how many times you want to measure it, because as you know, the IBM whatever systems, quantum system that we have access to, So those are noisy in nature. So as many times we will run, those would be the approx result. Okay. So in this, you are seeing the probability is 50-50%, exactly 50-50% in the probability section. Okay. But in once you measure it, you will not get exactly 50-50%. Okay. So probabilities would change. So that's why as many number of shots means those many times measurement you are doing. 1024 is the whatever it is defined by default. Okay. So you can increase it or you can decrease it. So if you are running very big systems, better increase it so that you can get very good result. Okay. So now if we go into details, one of the system I'm going the details into. See, let's see this one. Brisbane. This circuit, this particular map, today Kapil sir has shown you. This is the map. It shows that how the qubits are interconnected. Okay. So 0 is connected to 1, 1 is connected to 2, but 1 is not connected to 19. Okay. So that means that, it means that if I'm giving any circuit, suppose I have a circuit, currently I have a circuit 0 and 1, where 0 and 1 are interconnected with C node gate. Okay. So in that case, I can, of course, this is only 2 qubit gate. I can pass on to any quantum hardware that I have access to, because 0 and 1, or there would be any 2 qubit which would be interconnected. Okay. So in this case, it can go into any qubit and it can run very easily. Suppose you are going for the higher number of qubits, like you have 120 number of qubits in your circuit, and those some of the 50 number of qubits are interconnected. So you have to find out one of the hardware which is mostly interconnected. Okay. Or you have to transpile your circuit. You have to make some swapping gates, use some swapping gates, another C node gates, and then you have to run it. But you don't have to worry about it. Everything is actually, with the help of this transpile function, you can just use that transpile function. It will automatically convert your particular circuit as per the hardware requirement. Okay, you don't have to worry about it. And of course, this color. So some of the colors are dark blue, some of the colors are red, light blue. This shows the errors. How much error that particular qubit contains. Okay. So it also shows over here that this how it is going. Okay. So this we have to see before using any particular hardware. But in here, we do not have any choice, because Brisbane is using, there are 2,000 number of jobs pending over there. Qubit. No, actually this is not. This is the error of this particular qubit. Readout error. Once you do a measurement, you get some error in your measurement. Some noise, due to some noise this is happening. Exactly 0, 1, some changes would be there. So that's why we are saying that qubit, these hardwares are noisy, because physical error. Okay. So other things we do not have to go in detail, all those things. We just have to see what is there. Okay. So this is the basic actually composer. Okay. So in composer, we can also go on and create another set of circuit over here. Okay. But yeah, it's better if we go for the programming. In programming, we have access to lots of other gates as well, and we can use that easily. So this is a circuit. For showcase, I have kept it over here. This is a teleportation circuit, quantum teleportation. You understand that quantum teleportation happens in, Aniket has shown you that one person is on moon and other person is on earth, they're transmitting some more information in between them. So that happens with the help of teleportation. Okay, so I'll show you what it is doing. Okay. So this is the basic teleportation working. There is some source. This is some source over here, entangled photon, which is generating some entangled photons, and it is transmitting those entangled photons to two different locations. One is source, another one is destination. Okay, so A is going over there and B is going over there. Okay, now they have shared a Bell state. Bell state is the 2-qubit most entangled state. So they have shared that particular state. Now, what is happening over here? This source wants to send some kind of information to destination. Okay, so now they have shared their entangled photons. Now they have their entangled photon. Source is having its own entangled photon, and destination is having its own entangled photon. What it does, the source wants to send some information to the destination, but it needs to be sent in a most encrypted form. Okay, so for that case, source is doing some kind of transformation, some operations it is doing, with the help of which it is sending the information, okay, to the destination. Okay, so these are, so once source does some kind of operation, whichever with the help of information that it wants to send, and with the help of entangled photon which it is having, okay, it's done some operation. After the operation, because the source and destination share a single set of entangled state, so source, after those operations, source would be able to send that particular information to the destination without doing anything else. Okay, and of course this is not actually pure faster than light thing, because there is some classical information also passed, okay, from the source to destination. This is a very big quantum teleportation concept. I'm just trying to making it as simple as possible. Okay, so yeah, that data is moving. This is the classical channel, because after the operations, whatever operation source does, it has to transfer, the source has to transfer some classical information to the destination, so that destination can recover whatever information source wants to send. That was not the classical information, that was some of the quantum information. Okay, so this is the incoming photon. This D over here is some kind of information which source wants to send to the destination. Okay, so because they have shared this entangled photon A and B in between them, so with the help of once source, what it will do some kind of operation with the photon which it wants to send with the A, and with the help of, after doing those operations, it will transfer some kind of classical information to the destination, and with the help of that particular classical information, this destination would be able to recover the D photon, which which source wants to send initially. So as you can see, D is not getting transferred, only the classical value is getting transferred. So for that case, initially, okay. I have to, okay. Okay, so here, if you can understand, this Q0, for the time being, we are considering that Q0 is some kind of information which source wants to send. Okay, and Q1 and Q2 are the bell states or the entangled state which are shared between the source and destination. So for that case, to generate a bell state, we have to apply these two operations, Hadamard and C naught. Okay. After this Hadamard and C naught, these two states are entangled with each other. Okay. Is this clear? I know this is a tricky topic. Okay. Now, the operation, because this Q0 is the information that source wants to send. So source is the Q1 over here, and Q0 is some kind of information that source wants to send. So it will do some kind of operation. So these are the two operations the source will do. Keep in mind that Q1 is source and Q2 is destination. Okay. So these are the two operations which source will do. And after these operations, source will do some kind of measurement. Okay. Now let's see. Let's start with the Q0. I'm applying some Hadamard gate over here. On Q0. So Q0 is some kind of information that Q1 tries to send, source wants to send. So if you look into it, this particular block sphere over here, kind of circle over here, if you see, this is empty, this is gray. Okay, I'm applying a Hadamard over here. It is converted into half blue and half gray. That means it is in superposition state. After doing all these operations, if you see at the end, Q2, which was with destination, now it is same as the Q0. Oh, let me just, what is happening over here? See, this Q1 and Q2 are these entangled states. That's why these are half. Okay, and this is the Hadamard gate that I am applying. This is the some information that Q1 wants to send to Q2. Okay, so this after the Hadamard, it is converted into half gray and half white. So all these kind of operations, after doing all these operations, at the end, if you see, now Q0 is converted into gray, but Q2 is converted into half, which is same as this. So that means some information transferred over here. Teleportation happening. Okay. So this is what we can do with the composite. Okay. Any problem in this? Any question with this? Yeah, of course.
How do we see if I wanted to send? We are just like they're dropping Hadamard, yes, gates, gates.
How do we? There is a mathematics behind it. Actually, I don't want to go into that mathematics right now.
For every Q0, Q1, is that I should know the states and then identify H or Z gate and then finally.
So this is basic teleportation that is happening. Of course, who has discovered it? They must have known that this kind of thing is gonna happen. So Hadamard C naught is basically for generating the entangled state. And now what is happening over here? Hadamard and C naught is the entangled state. Now, the source will try to find something that somehow source has to send that information to the destination. So it will do some kind of operation. So for that particular operation, if you see the bell state, how do we generate a bell state? With the help of Hadamard and C naught. So in that case, C naught and Hadamard, if we apply in this order, that will not destroy the entangled state, but it somehow correlate this Q0 with Q1. Now Q1 already knows that Q1 is entangled with Q2. If that is correlated with Q0 is correlated with Q1, that Q1, whatever after the measurement, that information will be transferred to Q2 without doing any kind of work. Okay? Any other question? These are the classical operations. You don't have to worry about this. Just this thing.
ఈ ఎంటాంగిల్మెంట్ జరుగుతుంది హడమాడ్ ఆ తర్వాత
After that,
మెజర్మెంట్
We have to do the measurement. Only the Q0 and Q1. Because Alice is doing this. So Alice has to do everything. Bob has not has to have to do anything in here.
which can be accomplished using hadamat as well as
C note, yes. Yes. Okay. A little tricky, of course. So as you can see over here, at the end, if you can see, this is gray. Now this is gray, it shows that this information destroyed from here, but it is transferred to here. Okay, so this gray specifies that. Huh? Last are the some classical operations that we need to do. Okay, these are the classical operations. Okay, with the help of classical gates. Complete blue means this is a 100% probability in 1. Okay. So now what happened, because Alice has done the measurement, so entanglement destroyed in here. But we are getting this thing, and this is converted into gray. That means the information destroyed from here, but it goes to here. How much time do I have?
Now we can do deep.
We can give?
Deep.
Okay. Just a simple visualization I want to show you about the Hadamard and all those gates on the block sphere. A simple, I'll just take 5 to 10 minutes more. And simple visualization I want to show you, that those single qubit gate, because I told you guys that on block sphere we can see the single qubit only information about the single qubit. So on the block sphere, how the Hadamard is working, how those single qubit gates are working. So we will see over here. So it would be easy for you how this block sphere is also coming here. So this I show you this particular 0 in the upper side of the block sphere and 1 on the downside of the block sphere, north and south pole, and this vector is pointing towards 0. That means initially every qubit is in state 0. Now once we apply Hadamard, what is happening? 0 plus 1 superposition state. Now x, okay. Now there is one other thing. X here we represent it as plus state. Okay. So that means here is the plus state and somewhere around here is the minus state. And this is coming with the iota 0 and iota 1. Okay. That we have to keep in mind. Now if we apply Hadamard, that means that vector should move to x. So what is happening over here? This is 0, and after applying Hadamard, it is converting into x gate. So x is the superposition. So this we represent as 0 plus 1 by root 2. That's why this is x is also known as plus x, plus state. Okay. So okay. So now if we have our vector in 0, if we have a vector in 0 and if we apply x gate, what will happen? 1. Okay. Now it will, what it will do? It will flip. Okay. So let's see. It flipped. Okay. Now with the Y gate, this is a little tricky. But on 0, yes, but on 0. Iota 1. Okay, iota 1. But we are not considering iota into here. We are just considering the states. 0, 1. Okay. Now the Z gate. Pauli Z gate. 0, it is in 0. It will be in 0. Yes, of course. Now how to visualize it? What we can do? We can convert into it. So now point is 0 is 0. 1 is minus of 1. How to say it? There is no minus 1 we can see over here. So what we can do is, first we will apply Hadamard gate, convert it into superposition, 0 plus 1. Then we apply a Z gate. It will be converted into 0 minus 1 by root 2. So now this we have applied Hadamard gate over here till here. And later on, it will go to minus. Okay? Because I told you 0 plus 1 is around here on the x, and plus x-axis, minus x-axis is minus state. Okay. Okay, that's it from my side. Because I also have many other gates as well, the visualization of those gates. But those are the rotation along the x-axis. So I can show you those as well. So this is a rotation. So I showed you a rotation. If we have a phase gate with an angle of pi by 4. So somewhere in between it will go. So these we can see. So with the help of visualized transition, we are able to see those gates. How it will somewhere in between. Because that's why I'm not showing you, because it will go somewhere in between. Okay. Okay, so that's it from my side. If you have any questions, you can stay back here. We can discuss. Otherwise, yeah, tea is over here. Tea is outside. You can have.
Tea break.
While we are creating the